Let's spend some time to talk about some of the basic concepts in statistics that turns out to be very useful for our discussion on machine learning. Um, so we're going to spend maybe half an hour to talk about just to review some of the important concepts uh, in statistics that we are going to use later on once we start to talk about different statistical machine learning algorithms, right? In fact, many of those statistical machine learning algorithms are actually based upon the so-called Bayesian analysis. Um, and in order to understand this kind of a Bayesian paradigm for understanding statistics, we need to have a basic understanding about, for example, sample points, sample space, events, and probability, right? So let's talk about them. Let's talk about them. Saying what exactly the sample points, right? So suppose I have a dice. I have a six-sided dice, and I'm throwing the dice to do an experiment, and the outcome, the possible outcome of throwing a dice uh, could be like a 1 point or 2 points or 3 points, 4 points, 5 points, or 6 points, right? So any of those numbers, either 1, 2, or 3, or 4, or 5, or 6, is called a sample point, right? Um, a sample point is pretty much just one possible outcome of doing some kind of experiment, right? And if you don't think it in terms of experiment, you could think about realizations of a certain random variable. We're going to sort of talk about random variables in just a little bit. So sample points are probably easier to understand. It's just one possible outcome. And then sample space. Sample space is actually made up of sample points. So the set of all the sample points gives you the sample space, right? So what's actually the sample space for throwing a dice with six sides, right? It's the set of the six numbers, either 1, 2, 1, 2, 3, 4, 5, 6. The set of the six numbers is actually the sample space, right? So if we use a graphical representation, suppose that's the line, right? And then we have like six integers on it, 1, 2, 3, 4, 5, 6, right? And the sample space is composed of these six discrete points, right? The sample space for throwing a dice. Um, but we have to also think about um, other kinds of possibilities, right? So we need to generalize our understanding of sample space to in two different ways. First, let's think about it. If I suppose I have not just one dice, I have like two dices, right? I have two dices, and I'm throwing the two dices together, and then that's what's gonna be the sample space for the outcome of throwing two dices together, right? And in this case, we have to account for all possibilities, all combinations of the outcomes of the two dices, right? So one, for example, one possibility is the first dice comes out to be like 4 points, and then the second dice comes out to be like 2 points, that kind of thing. And then um, in order to actually represent a certain sample point, you cannot just use one number anymore, right? You have to use two numbers, right? Two numbers combined together is pretty much just a vector, right? It's a vector on a two-dimensional space, right? So suppose the horizontal axis is the outcome of the first dice, and the vertical axis is actually the outcome of the second dice, right? And in this case, the first dice could take upon six different values, right? And then the second dice could take upon six different values. So in total, we are going to have like a 6 by 6, 6 times 6, that's 36 possibilities, right? So we have like 36 points in this kind of two-dimensional lattice, right? So the sample space for this kind of two dice scenario is going to be this two-dimensional lattice, right, with 36 points, right? That's the sample space for throwing two dice together. And you can sort of generalize even further. Suppose I'm throwing like three dice together, right? And then what's going to be the sample space, right? Then it's not going to be just a lattice in two-dimensional, right? It's going to be a three-dimensional lattice, we have one more dimension that goes out of the screen, right? And then it's gonna be like more like a three-dimensional cube thing, right? With all those points that's located at the intersections of the lines, right? And you can generalize it even further, right? You can generalize it even further. Suppose I'm not throwing three dices, I'm throwing like more than 100 dices together, right? Then what's gonna be the sample space, right? If I'm throwing like 100 dices together, then it's gonna be a 100 dimensional hyperspace, right? It's gonna be a lattice in a 100 dimensional hyperspace, right? And then you can even generalize it even further. Suppose I'm throwing an infinite number of dices, right? Then what's gonna be the sample space? It very quickly will go out of the. We won't be able to actually draw those sample spaces on a two-dimensional surface, right? We have to actually imagine them in our heads. So that's the generalization in terms of dimensions of the sample space. And another thing is that another direction for generalization is that it doesn't have to be discrete, right? It could be continuous. The value doesn't have to take upon just the discrete numbers, right? If you are throwing a dice, there's no possibility to give you a value that's like between 1 and 2, right? But in um, in many applications, the outcome could take upon a real value, right? A continuous value that between a certain kind of interval, for example, 0 to 1. Right? One example that I myself often use is the porosity values of rocks, right? So rocks are not exactly like a solid. Uh, it's not exactly like all solid. It's got lots of voids, lots of empty spaces in the middle. And if you look at them under a microscope, you're going to discover lots of pore spaces, right? And then the porosity is basically just the ratio of those pore spaces with respect to the volume of the entire rock, right? So it's going to take upon any kind of a continuous value between 0 and 1. It's a real value number, right? So if it's actually porosity for a point underneath the ground, right? Then the outcome could be like a continuous number between 0 and 1, right? And the same is true if I want to generalize the dimensions. Suppose I have 2 points underneath the ground, and the porosity at those 2 different points is going to be the sample space for the porosities at those 2 different points underneath the ground is going to make up this kind of rectangle or a square, right? Square with it's a 2-dimensional square with the interval between 0 between 0 and 1, basically, for in the horizontal direction and also the vertical direction, right? And suppose I have more than 2 points. I have like 3 points, 10 points, 1 million points. Then it's gonna be like this kind of hypercube in those kind of multiple dimensions, right? So the sample space looks like a very simple concept, but we have to actually generalize them and then think about sample space in multiple dimensions and also sample space for discrete and continuous values, right? And then event, what exactly is an event, right? Event is basically just a subset of the sample space, right? So in terms of events, we can have an empty event, say A equals to the empty set, right? We can have elementary event if we have just a single sample. If we have just a single sample point in our event, say A equals to 6, B equals to 2, that's for throwing a dice, right? And then we can have composite events, right? So if you have like multiple sample points within an event, then it's a composite event. And we can have a whole event. A whole event, which is usually denoted as capital omega. It's a Greek letter, capital omega. It's actually the entire sample space. The whole event, it's actually the entire sample space, right? Once we talk about these kind of subsets, we have lots of mathematical operations, right? For example, we have union, right? So suppose A is 1, 3, 5, it's a set, right? And then B is another set that's 1, 2, 3. Then the union between A and B is going to be 1, 2, 3, 5. And then we can take an intersection between the two sets, right? So the intersection between these two sets is going to be 1 and 3, right? That's the two common elements between these two different events, right? And there's a suite of mathematical operations that we can apply on different on those kind of sets, right? On those events. Here it's a graphic representation of those mathematical operations. So suppose this is event A, right, and then this is event B. They have some overlap, right, and this overlap is called the intersection, right, and this intersection can be computed by taking this intersection operator. That's the intersection, and then that's the union. That's a union. It's a combination without duplication of the intersections, right, and then complements, right. What exactly is the disjoint events, right? What are disjoint events? Disjoint events means that A and B have no overlap, right? That's called disjoint events. Right? And then here are some more complicated examples involving a third event, C, right? It's not just A and B anymore. It's A, B, and C. Three events can interact with each other and give you all sorts of strange shapes, right? That you can actually obtain by carrying out those complicated examples, right? So some of them are called distributive law, right? Distributive law 1, distributive law 2, right? De Morgan's law, De Morgan's law 1, De Morgan's law 2, right? If you are interested, you can actually look into it. So C actually represents complement, right? And then you can actually try to understand how those, or try to actually come up with a proof for all those different results, right? Here, so it's not too difficult, but we are not going to talk about it in this particular video, right? And then probability, right, which lies in the heart of statistics. What exactly is a probability? Probability is basically just a measure of likeliness that an event will occur, right? And this kind of a definition is based upon our intuition, our sort of intuitive understanding about what probability actually is. It's a measure of likeliness that an event will occur, right? And then statistics are based upon three axioms. So those axioms are not actually proved, but they are actually considered to be true. And then all the mathematical derivations are based upon those axioms, right? So first of all, the probability, which is written using PR, these two letters, right? The probability of a particular event A is going to be non-negative. It could be larger than, it should be a value that's between 0 and 1 inclusive, right? And then unitarity, right? The probability of the whole event, capital omega, should equal to 1. And omega is, capital omega is the whole event. That's the entire sample space. And additivity. So the probability of event A1 union, event A2 union, event A3, and then goes on, should equal to the probability of A1 plus the probability of A2 plus the probability of A3, and goes on if all those events are disjoint, right? This is based upon the assumption that events are disjoint, so they have no overlap, right? So if there is overlap, we have to actually subtract the intersections, right? So these three are basically just the axioms of probabilities. Some more concepts, right? Some more concepts that we're going to use later on. One is called the random variable. What exactly is a random variable, right? So for students who are kind of new to the concepts of statistics, they think the random variables are something that's kind of out of humans' control. It has to be decided by God or some kind of transcendental value or transcendental power, right? But it's not true. Random variable can be any variable as long as a probability is assigned to each realization of that particular variable, right? What I was saying, for example, the porosity at a certain point underneath the ground, you can consider it to be a random variable, right? But if you actually take a piece of rock out of that point and then measure the probability, measure the porosity, you could actually get a deterministic value, right? Even though that deterministic value can have uncertainties, right? You can have measurement errors, that kind of thing. So random variable is decided by you. If you want to assign probabilities to different to each realization of a particular variable, then you can consider it as a random variable. And then we have a suite of mathematical tools that we can use to study those uncertainties and study those probabilities, right? So random variable is actually a very general concept. You can treat pretty much everything, even things that you consider to be deterministic, you can consider them as random variable, except that maybe the uncertainty is particularly small, that kind of thing, right? That's called a random variable. And then probability distribution. So probability distribution is merely just the mapping. It's a mapping, so it's a function, right? A function is a mapping. It's a mapping from any realized value of the random variable to the corresponding probability. So PR x is any of those realized value, right? The probability of taking upon any of those realized value equals to fx. Fx is a function of x, right? And fx is considered to be the probability distribution. Right? It's a mapping between the probability, right? The probability of a particular realized value of the random variable. Right? It's a mapping between from any realized value, which is x, to the probability of that realization. Right? So that's what we call a probability distribution. Right? And once we have the probability distribution, or fx, we have to sort of make a distinction between the so-called probability mass function and then probability density function, right? Which is basically just for discrete or continuous cases, right? So if we're throwing a dice, for example, right, and if suppose the dice is fair, it's not loaded, then the outcome of the 6 numbers should be equal, right? It's 1/6. The possibility or probability of the outcome for the 6 numbers should be exactly 1/6, right? If the dice is fair. And then here is some sort of a histogram representation for the probability mass function, because in this case it's a discrete case, right? So the x values is discrete. It's 1, 2, 3, 4, 5, or 6, right? And then the height of each of the column is exactly 1/6. 1.667, that kind of value, right? So it's a 1/6, and then the summation over all possible realized values of the probability mass function should equal to 1, right? And then that's the discrete case, and it's called probability mass function, right? And then for the continuous case, all we have to do is to actually change the summation to the integral. We just integrate over the entire sample space, right? And then the integral of the so-called probability density function fx, it's continuous now, it's called the probability density function, should also equal to 1. Right? And here is a graphical representation of one example of the probability density function. So the x value could take upon the sample space is on the real line. It's a one-dimensional sample space, right? It goes from like a -2 to like a more than 6, right? And then the probability for this particular range is like a 0, right? And then for this particular interval that goes from like 0 to 1, the probability is like a 0.5, right? And then turns back to 0 again, right? And then once it reaches 4, location 4, the probability jumps to 0.5 again, and then lasts for like a 1 unit, and then turns into a 0 again. So it's a continuous function, even though it looks like it's kind of a discontinuous function, right? But the probability is still a continuous function, so it's a probability density function, right? And then for probability density function, the probability for the outcome to take upon a value between a and b inclusive is just the integral of the probability density function from a to b between the two boundaries, right? one very interesting observation is that what's going to be the probability for x to take upon a specific value, say b, right? So x is larger than or equal to b and smaller than or equal to b. So x has to take upon the exact value of b, right? So if a equals to b, then it's an integral from b to b, right? And then an integral from b to b, actually, for any kind of probability density function, the integral from b to b is going to be 0, right? So that's some kind of a counterintuitive effect, right? So it depends upon how you actually define integrals also, right? Um, it's there are some deep mathematical results um, that allows us to actually understand this kind of phenomena better, right? So, but in our usual sense of definition for probabilities or probability density functions, then the probability for x take upon a specific value is actually 0, right? So this is counterintuitive. So that's it for today. Next time we're going to talk about um, some mathematical formulations of Bayesian analysis.